Okay, welcome to today's webinar. The topic for today's webinar is stress analysis of surfaces and members in RFEM 6 and RSTAB 9. My name is Caroline Lessmann and I'll be your moderator today. I work here at Dlubal Software in the marketing department, so I'm responsible for the webinars and newsletters. And yeah, my two colleagues will present and answering your questions today. And yeah, well, they can introduce themselves.
Hello, I'm Andreas Niemeyer. I'm presenting today's webinar, and I'm responsible by Dlubal for the product development. Here I lead together with Mr. Dlubal all best features and transform it to the programmers.
So hello, my name is Stefan Hoffmann. I'm working in the customer support and I'm also responsible for the development of the dynamic analysis add-ons, and I will be sitting in the chat and trying to answer your questions.
Okay, thank you for your introduction. Now we can switch off our webcam so everybody can see the full screen. And then just for your information, we always encourage you to ask questions throughout the presentation. So here on the right side of your screen, you have the control panel where you can ask your questions here. And yeah, if by chance we can't answer all the questions throughout the presentation, you will certainly get an email afterwards. And the other way is to watch the entire webinar and send your question after at info@dlubal.com. Okay, so that's from me now, firstly, and then I hand over to my colleague, Andreas Niemeyer. Andreas, you're muted. We can't hear you.
Thank you. Thank you, Caroline. Okay, I start again. So thank you for overtaking. I start with our topic today, stress strain analysis in RFEM 6 and RSTAB 9. My task is, or my aim is to show you what you can do with this program, what you can design and what the limits are. For this, I have a short agenda. Let's say which elements we can design, what are the new elements you can design, and how you can document it. Of course, in my style, I always want to present all these features in a short story, and therefore I prepared some elements, or let's say models. And for this webinar, you will find it also on our website. For this webinar on the bottom, here my colleagues already uploaded the models I want to present today. And we will start today with a, let's say, a facade model from members. Here we try to design, we model it and we try to design the members by stresses. Then we go over to let's say, fix this facade on the concrete slabs by modeling such a console. Here we take care about design of surfaces and design of welds between this angle and this ear sheets. And at last but not least, we take a look on a solid model. Of course, I want to show how you can let's say, design such solid models with the add-on, how you can detect stress ranges, and how you can do solid sections. And let's say this is for introduction, what we want to do in the next hour. And now I change directly to RFEM. I prepared an open RFEM here. Of course, we can start now modeling this facade by giving this grid. But I think when you're starting modeling facades, you always will start with a drawing from the architect or whatever. And I prepared such a drawing in AutoCAD with 2 layers, one with axis, one with facade. And I overtaking this geometry directly from the opened AutoCAD sheet into RFEM by using the import function. Here, this direct interface to AutoCAD. This is, I think, quite comfortable because you don't have to take care about geometries and you can overtake it directly. The only question what the program wants to know is how it should orientate it, because AutoCAD have a different coordinate system like RFEM, but our developers implemented here a nice option to rotate or mirror it. And for this model, I would say the y-axis is C, and the z-axis we will mirror. And to be organized, we say, please overtake the layers from AutoCAD into visibilities what is similar in ours. And if we overtake it and confirm the dialog, you will see the facade will appear in the background. And of course, like expected, we will get here in the visibilities 2 user-defined visibilities, 1 facade, so this means the outer layer, and 1 axis layer. For our purpose today, we only need the axis layer, so the facade part we will delete. I select it and remove it. So now we know exactly how big the facade is, what are the dimensions, what is the grid spacing, and we can go ahead modeling this structure. And for this, of course, we take a closer look on this model and see, okay, the draw of this facade, did the lines from left to right and draw over this mid elements. This is not really suitable for RFEM because you have to define here some contact definitions. So we repair it with this intersection function and create here single lines. In the next point, we try to add members with suitable cross sections, and for this I prepare material and sections before. Therefore, I open here this material table. You see the program already defined a steel with sections from the AutoCAD drawing, but we don't need a steel, we need an aluminum here. Therefore, I delete this import and define here a new material by using this keyword search 6060 and select here, for example, this T6 aluminum from Eurocode solution and confirm it. And next point, I go to the section register and define here the cross sections. These 2 drawing philosophical sections I delete and define 2 new one for the columns and 1 for the horizontal elements. For the columns, I open the library, and because it's an aluminum facade, I have rectangular hollow section, and we prepared for this stuff a special cross section. It's here because it's a rectangular hollow section where you can specify the thicknesses individual, what allows you to simulate all these cases simplified. And I define here as high 200 millimeters as with 60 millimeters for the thicknesses, 3 millimeters in both directions, and for the, let's say, short thicknesses, I use here 5 millimeters. And because we have a similar cross section for the horizontal members, I select this already defined cross-section, copy it and modify it that it fits. So I change it here to 180. Okay, now we have prepared everything. We can assign it and we can start assigning. So I select here these vertical lines by pressing Ctrl at the same time and go here into the properties of the line and select here the option member. This is designed for RFEM, that it knows, okay, I have to apply now a member with a specific type. We use here beam, and as cross section we use the first one, and after confirmation the program is distributing this cross section to this line. The same we will do for the horizontal elements. So we select it, right click, edit, members, the same action like before. The only change is here that we use this second cross section. So far was everything easy. If we take now a closer look to this facade, we will see that the program have here rotated the cross section in a wrong orientation. This comes from the basic definition, how the members are placed in space, but it's not a big deal because we can open here the section list, can select both cross section and use here the section rotation and define here, for example, 90 degree. After confirmation, you will see the program is orientating the cross sections as expected. So far, we have defined now the grid of members, and we can start adding additional properties like, for example, hinges, and bring in some organizational stuff. And for this organizational stuff, I would to say, for me it's interesting now, when I draw with my mouse cursor above these members, you will see it will be only selected these elements between these horizontal elements again and again, but in reality these elements belongs together because it's manufactured from one beam. Therefore, I select all these members and say in the properties or in the context menu, members, please be a member set. The program realizes 4 different settings, and now we have defined it as member set. In the next fact, I want to introduce a news, or let's say a special feature from RFEM, what should help you for organization of structure and further also for design. And here, please open the base data and open the settings and options register, and you will find on the bottom here 2 options, member representatives and member set representatives. We will, let's say, activate both, and if we confirm it, you will see you will get here such red bubbles above the members, and you will get here 2 arms with a setting. And this means the program realized now we have here similar elements for these horizontal elements, and we have also similar elements for these vertical elements, and it could be much more. So this means the program realized now 2 unique positions from these 24 different members. And this is now easy because we can use these settings for, let's say, defining some stuff, for example, hinges. I can select all by using this option and say, yes, of course, we have a hinge on both sides. And later we can use this definition for reducing my documentation, because I can document only these 2 elements because it uses the biggest forces of all available elements and outputs it in this definition. But I will show you when we have these results. Now the structure is so far ready to apply boundary conditions. Here I starting with the load boundary conditions, what means we create the load case self-weight and wind. For self-weight, I open here the list. We can define here name, self-weight, and when we take a look, of course, the self-weight is activated here, but we have also to consider the weight of the glass. And if you have to model such a facade, you know, the glass is not inside the members, then it's in front of the members. Therefore, it bring us a torsion bending moment on these horizontal elements. And how we can consider this? We can consider it with a load, and to know where the eccentricity should run, we activate here a member axis system. This shows us, okay, for all elements, the z-axis show inside the monitor. So if we assume the glass is in front, we have to define the eccentricity in minus z direction. Now, let's apply the load of the glass panels in front of the facade, and here we take a member load with a type NX, where I can say, okay, here let's define here 3.75 kilonewton, 2 pieces of it, and we place it here in 10% of member length plus 80. And we define here a load eccentricity, which should run in z direction with minus 160. So now we can say, okay, this load should be applied on this member, and for the others we do it similar. So if we closed the dialog, we can overtake the basic settings from with this overtaking function. And now let's write here 0.2 for the small panels. So let's select here these members, apply and next, and the last one is 1.7, and here are these 3 members. So this was a quite easy task to apply such loads, such dual pitched loads. And now we go over to the next load case. For me, it's important now to present this steel, this stress strain add-on, to have some different load cases. So we need something. So in this case, it's a facade. We apply a wind load. Here I use the category wind. Okay, and let's apply the wind with a wizard. Here we offer a member load from area load wizard, where we can say the load could be, for example, 0.7 kilonewton per square meter. It should run in y direction, and it should act on all of these cells where I draw a window above. And now, after confirmation, we see a symbol which symbolizes this load, and behind, if we display it separately, you see it will distribute it as expected to the members, but for a simplified display, we can use this picture here. Now, we are almost ready. The only point what is missing is the boundary condition for the support. And here we take a look. Maybe let's use here this global coordinate system, and for this we support it in the middle, so here, and therefore I select this member and divide it in the middle by one node. Of course, the member representative remains because it belongs to the member set. And now we can use these nodes and can apply here nodal support, which is fixed in x, y, z, and the rotation about z. And so far I can fix it on this slab here. And for the bottom, we take a similar boundary condition. The only thing what I do here, I release this heat degree that I have a free movement in this direction and apply it to these nodes here. Now my structure is almost ready. We have supports, we have floats, we have a structure from members, we have member representatives, and the question could arise how I can design it according stresses. To design it according stresses, we need a combination of loads. What means I want to combine it according to this rule. For example, according Eurocode 0, I use a wizard for it. And the wizard, let's say, thinks we have to do a complete job. So it offers us ULS and SLS checks. For me or for my presentation today, only the ULS checks are important. Therefore, I remove it. And this means now with this setting that the program generates combinations according to this law here. You see also this box is empty here. There's a lot of free white space. The question why I will answer directly. But if we go to load combinations, you will see the program creates us here these load combinations according to these defined loads. But how I can say the program that it should do a stress check for these members. And for this, you have to open the base data and have to go to the add-on register and open here, or let's say activate here the stress strain analysis. For me, it's now good for the presentation that I activated afterwards, because when I activate it afterwards, we get here a new calculation task, we get here a new table, we get stress strain analysis arm here in Navigator. But in this combination, if you go back to design situation, you will see suddenly we get here option stress strain. And this is governing, or let's say a really important fact, because now this design situation, DS1, including these combinations, knows it should run a stress strain analysis. Of course, I can deactivate, but it knows it should do. And if we calculate all, the program runs all available load cases and combinations, and afterwards it runs a stress strain analysis. So static analysis is done, we get deflections and forces and so on, but now we get also here a result stress strain. So this is, let's say, the game behind. You define in basics data the information what you want to calculate, and the design situation is, let's say, the basket of forces what will be moved into the stress strain analysis. And to understand it more in detail, we open now the table of stress strain, the input data, and here you see it's matching. So in the first table you will see DS1 is activated. In the second table is activated what should be analyzed. Here you see we have members, member sets, member representative, member set representatives. Everything is checked. This is standard setting. For you, it's important. You see the program will design everything what it will get in hand. So we have these objects here. These objects will be designed. In the next option, it will offer us to calculate not only stresses and also stress ranges. It's deactivated because it's not a standard what you have to do, but you can do. I will present this option with this solid example. And in the next table, because this stress check is not only calculating the existing stress and also the limit stress, and therefore it mentions here the material what is used for the cross sections. The same for cross sections. And now we coming to a, let's say, a main table. Let's say the brain behind what decides what should be calculated in this stress check. At the moment you see in the navigator, it calculates for members, for member representative and member set representatives, sigma tot, tau tot, and sigma meses. but you could calculate much more if you want. So here, if you open this setting, it's something like calculation details for the stress strain check. And you see, oh, you get here a really long table of stress components, what you can calculate: normal stress component, compression stress component, tension, bending. And here the program activated sigma tort, tau tort, and meses. And on the second column, you can select what should be checked: limit equivalent stress, for example. But you could also use user-defined if you wish. And so far, if you define this, you see this is not only one setting, then you can have several. For example, we give here a name, meses, and we use a second, for example, Tresca. And here for Tresca setting, we define here Tresca option. And now if we confirm this, program wants to delete results, and we can say now this Tresca option should use, for example, for these 4 members. What happens? The program says, okay, this member blah 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 should be checked with meses setting, this member should be checked with Tresca setting. An overview of all this you will get in the last tables. For example, members, you see member 1 is checked with this, member 6 with this. So you get an overview here in table, but of course you will get the result of all these settings here graphical also, because here in the results now you get not sigma tort and tau tort, then sigma meses and Tresca. Meses is defined for all, Tresca is defined only for these 4 members like we did it. And because this is only the existing stress, you can also visualize the diagrams on utilization. So here you get the utilization visualized here as diagrams on members. Now, if you watch all these results, you will see we have stresses on members. This will be distributed in different, let's say, ways. For example, stresses by design situation, the stresses by loading. You see this load gives this result, this load gives this result. By material section, and so on. For example, by location on every X place. Yeah? Then you can go through every X place of stress. And if you say, oh, this stress is interesting, I want to know more in detail, you can open here the details, and you will get an environment which shows you for these coordinates, the material properties, the section properties, the forces on this X place, and the stresses, and the formula which leads to this utilization. If this is not enough and you say, I need it more in detail, you can open the, let's say, cross-section layout and get the utilization or stresses visualized over the discretization of cross-section. Here we have a stress layout, here we have a utilization layout, and if you're interested in stresses itself, you get also stresses from normal force, stresses from bending moment, stresses from normal action. So all these things you can display if you need it, but in standard you get everything visualized as these diagrams. And now you see, if you watch all these results, endless results, we know as engineers the biggest one is interesting. You get it here, and if you need it for different positions, let's use these representatives. Because this representative says you, here this member, this is the biggest result for this horizontal element, and this is the biggest result for the vertical elements. And if you visualize it here, not by members and by representative, you get the biggest result overall visualized. So everyone has the same result because it's unit or not Unix, and it's representative of all these members. So this brings me to the end of this example. I want to show you here, maybe to repeat, how you can model a small member structure, of course, and how you can make a stress check for these members and representatives. And now we want to extend it, how you can use this add-on for a surface model. And we imagine we have to fix this facade here. We read in static analysis that we get here, let's say, forces, maybe 16.3 kilonewton downwards and 14.3 kilonewtons out of monitor, and we have to overtake these forces from this frameworks model to the concrete slab. And how we can do this? Here I copy me such a member in Windows clipboard with Ctrl+C and open a new file. File is the wrong word, model, and we say here K5, for example, and activate directly stress strain because it's our task today. And we confirm this and we get an open model, and now we set our focus in the middle and press Ctrl+U. The program asked me if he should give an offset for this model. I don't want, and get this member fragment here in my model. If we display it as wireframe model, you see it's a member with a cross section, and if we select this member and go into the context menu, you see we get an option generate surfaces from member. This gives us now a discretization, a surface model discretization of this cross section. Here we have the surface thickness 3, here the surface thickness 5. But in fact, we need only the floor plan of this structure. So if we take a look here, maybe let's deactivate this table. We have now to fix this facade to the concrete slab, and we have to model here a console what can overtake this. And this is my basic geometry what I should overtake. For this, I select this line here and say, I have to move it maybe in right direction, and we copy it. We use millimeters for better description, and we move it in X direction. We know plus 1.5 because it's a half of this 3 millimeters, plus the thickness of the console maybe 10 millimeters and a half of 5 millimeters. And I can calculate directly such inputs, and with confirmation we get the line on the right side. The line for the left we can copy by drag and drop. Now we know this, let's say, surface members here don't have to run completely to the outer edge of this cross section, so I shorten it a little bit. In this case, I don't create a copy, and I change it here with minus 30 millimeters and confirm it. For the other side here on this place, I select this nodes, and I have to maybe to extend it to connect to the concrete slab. So I use here also a modification in y direction with minus what we need here, minus 2.5, minus 50, and minus 5 again. And then these elements will be extended here. Now let's create the first metal surfaces. Therefore, I select both lines and move it a little bit upward at first, here with minus 50 millimeters. And now we draw from moving it down with a copy with 100 millimeter, a new surface by defining the vector, and here by using step links, by saying please create a surface in between, and if I confirm it, I get here my surfaces from these elements. Now we can create, let's say, the first part of the angle, what connects to the concrete. Here I use a function create node between two elements. for example, here this, and we create the standard node and apply it. Now we can copy it directly on the bottom, and we move this 10 millimeters above. So we say here -10. Okay, and the same for this node here, also 10 millimeters. Now we know the height of this back element. We move these nodes now finally here in X direction, for example, 100 millimeter in X direction, create a line in between, and then we draw a new surface, create copy with, oh, I made an error, I think, again. This is 10 millimeters, I should remove. Okay, now we can make a line in between and draw a new surface by using the vector -200 millimeter, create copy using step links with a new surface and connecting it. Then we have almost all elements done. The only thing what is missing maybe the upper part of the angle, and here we use the copy command again. We zero this, and in Y direction we use -150 and creating a new surface. So far, this was the modeling of such a console. Pretty easy, I would say. At the moment, the surfaces are red because they don't know its thickness. We select now both and define these surfaces and define here for stiffness type standard and assign here a new thickness with 10 millimeter, and we would like to have here a steel 235 from Eurocode, for example. Now, so far this is assigned and the console appears in blue. In the next point, we should take care about boundary conditions, how it's fixed. We know this angle will be supported on concrete, therefore I define for the surfaces or display the coordinate system. I see it's showing in direction to concrete. I select both surfaces and define here edit a support, and I select here support condition. I don't check it because I think it's unrealistic. I define here a pretty stiff spring and say it should act only in direction to concrete. In negative direction it should fail. And we have here these springs. In next situation I have to take care about, because it's not supported but it can removed, so I have to fix it against tension, so we have to use anchors here. So I use this corner node, create here a copy with -50 and in Y direction with 50, and let's create a node. We get it here, and the same for this node where we only change here this minus and get here the place where the anchor should be placed. The anchor have a diameter of 10 millimeters, so let's define here a hole. We pick this and define here a radius of 6 millimeters, for example. The same for this. And we know now this node will be supported. We have to transport the forces from this element to this node, and for this I use a so-called coupling element. I use here a surface condition with stiffness type membrane without tension, so it can only transport compression force in membrane direction. And for this we create a new thickness with 10 millimeter and a new material, again from steel to S235. Okay. Okay, and now we place this surface inside this hole. Now we can place a nodal support here. We define here an let's say nodal support without rotation fixation and place it on this situation. And now we do a second. The only difference will be that we release it in X, that we get no how to say strain or unstatic or unrealistic stress in between. So now we have modeled this situation. In the next instance, we have to model the place, or how to say, the load introduction. So it will be introduced in the center of gravity of this floor plan of this column from what we copied initially. And for this, I create only a short member here. To know the intersection points, I draw a window above this line, and you see it will cut it directly with the cross section. The remaining elements I can remove. And now I select these lines and give these lines here a member stiffness. I say it's a member, and because it should only transport forces, I use here a rigid member. And now I can place my load on the middle point, and this rigid member will transport it to this surface model. The only thing what is missing is that I have to introduce it here to this surface model. Therefore, again, I model here a hole with diameter of 20, so I define a radius of 10, the same on this side. Okay, and let's introduce again here this membrane without tension with this thickness number 4 and place it here inside this hole. Now the model is almost ready. We should define only now these forces from the facade, and if we remember right, we have 16.3 kilometers downwards. I use this component solution, so 16.3, and in y direction we have, I think, 14.3. Now we place it here, and you see the game. We place it here. The load will travel into these sheets and will be moved to this surface support and nodal supports. To get good results, we should mesh it fine. So we go to our mesh settings and define here, for example, a mesh of 10 millimeters. If you see this mesh, it looks globally nice, but I expect that we get here some singularities. So I refine the mesh on these nodes here, right click, edit, and we say we have here a mesh refinement where we say please place something like a globe or sphere around where the mesh will be reduced to this size. And the same is on these connection lines, because here we also play some music, I would say, where we say we need here a refinement. So let's take a mesh refinement, define here a condition, maybe target length is 5 millimeters. And now if we mesh this model, you will get something what is expected. It will be refined here, it will be refined here. So far it looks nice, and if you don't want to see these symbols, you can remove type for nodes, for example, and also type for lines. So far. Now we can, let's say, start calculation. But the only thing what is missing, we have to learn the programs that this loads, this 16.3 and 14.3 kilonewtons are already contains gamma factors. For this, we should remove this wizard. we should say this load case is fine, and here we will only take a look on this ULS setting. Service stress strain is activated, and this should be done for a load combination with DS1. And here we say, please consider this load case, because it could be done linear. And if we calculate all, we get the static analysis is mentioned with SA, and the stress analysis. From, let's say, plausibility control of static analysis, deflection goes downwards with 0.3 millimeters, it's fine. And the support forces, maybe contact forces, is also fine. It will be pressed against concrete and supported here. So far, I would say model is reacts as expected, and from stress strain analysis, you will get here, similar to the member model, a selection of stresses, maybe mesostress for stresses. Maybe take here stresses on surfaces, the existing one, and utilization against the limit stress, where you get the utilization. Now, what is a little bit disturbing is when you read this utilization, or let's say these stresses, you see you are almost by 600 Newton per square millimeter, what is pretty high. If you want to search where is this peak, you can define here a limit with 235, what creates you a special panel what running to red until 235, and the peak over is only this dark red, and you see how it's only this singularity here and here. So I think you can optimize by displaying only these elements what should be designed, so surfaces, stiffness type, standard, and you see, okay, now we have not 600 and 430, and the peak is here. How we can remove it? Of course, it's let's say a singularity, but in this case, for example, you can use a nonlinear material to use a yielding effect. For this, we are activating here nonlinear material behavior and activating it for this material here, nonlinear elastic surface solids. And if we rerun now the analysis, you will get, let's say, for the stress, for the existing stress, something to the yield stress, what means we have now here a yield stress as 235. So far, results okay. But the question is, do we have a yielding effect? And we have to check it. And this is now also the cause why the add-on is called stress strain. You can calculate with the add-on also strains. It means you can activate it in the global settings. And if you go to the surface configuration, similar to the members with this table, you can say, please calculate only sigma equivalent meses, and for the strains, please calculate epsilon meses and compare it if there is a plastic strain with 50 promille, for example. And now, if we calculate this add-on again, we get not only stresses and utilizations, and also strains. And you see, okay, your strain is here by 1.9, so far everything fine. And you can check it here. So now we come to the point that the surface is fine. We have to take care about next topic, what means welds. If you have to weld these elements to the angle, we offer in RFEM 6 a new solution. It's hidden here in the types for lines. You can place here line welded joints. It's a typical post-processing effect, what means you can define how the weld is looking like, if a butt joint, corner joint, lap joint, T-joint. Here you can say, okay, the shape is a single bevel, double bevel, single J, or a double fillet. You can specify the size and you can place it here in between, where you say this line, this element should be connected to this element. The same for this element connected to this element. And similar to members and surfaces, you have a stress-strain analysis where you can specify which element should be calculated. The program offers you, or it calculates, it transforms the stresses on the edge of the surface to a normal load, bending load, shear along line, and shear perpendicular to line, where you can say, please use a smoothing or no smoothing, and do you want to use a simplified or directional system. And here, if you calculate the simplified system, you get a normal stress, a bending stress, a shear stress, and let's say a shear along weld line, and finally here an interaction of everything where you can say, please check this value against allowed limit weld stress, for example here 208. It's calculated according to the formulas from Eurocode, but you can use it for all other standards, therefore we did it open. And when you calculate this, program deletes results from stress strain, and after recalculation you get here a result for surfaces we deactivate and a result for the line welds. You see here normal stress, bending stress in X direction, surface stress in X direction, shear in vertical direction, and the interaction plus a utilization. And where you see, okay, here we have a small peak what is overutilized. If you see these diagrams, you ask, okay, it's nonlinear, clear, but if you do a hand check, I distribute it over the complete length. I know, therefore we defined here in the line welded configurations, or we give you the option here in special options register to say, okay, please smooth the normal load linear, the bending load constant, and the shear loads also constant. And if you check this and recalculate the stress strain result, you will get now, let's say, a suitable result, because the shear load is now constant. Oops. And the, let's say, normal load will be distributed linear, and this results to a better utilization, and you can do the check. But it depends really on which stresses you use, if you use a smoothed or not smoothed. So now we come to the next chapter. Here, maybe to repeat, we designed surfaces and line welds with stress strain, and now one object is remaining, a solid element. And for this solid element, I prepared a model because I have not so much time today. I prepared here a small knuckle. Where it is, desktop, knuckle for webinar. No. Again, open. Stress strain. Let's open it. And here you will see a solid model, maybe for overview, remove mesh, remove load. It's made from surfaces with thickness 0, and I filled in a solid condition. The model will be supported here with a surface support in this hole and this top and bottom surface, and it will get a load maybe downwards and upwards to create different stress situations in this model. If you calculate or display, make a plausibility check of this model, you will see the deflection is going downwards. What is clear? Yeah. And for checking loading boundary conditions, you will see you get the restrainment for the top surfaces, pressure here, and in the inside, in the bearing, you get also pressure vice versa, transporting a bending moment. So far, it's reacting fine, and it will give you, let's say, stresses in X, in Y, and Z directions. You get extreme stresses, what is interesting for design, and you get also here strains. So it's different to maybe members. You get directly here internal forces, this like stresses, what is, let's say, logical for solid elements. And the program will display you these forces, or let's say stresses, on the boundary surfaces. If you want to look inside, you can create a result section and can define a cutting plane in structure. For example, we cut here in X direction. Then you create here a view inside the model. But all this, let's say, output gives you only the result of this selected load situation. If you have more and you have to do a design, the question appears how I can do a design. And this is the task of stress strain, because the stress strain add-on gives you the option to check amount of or a series of load situations and gives you the biggest stresses from it. So if we have, for example, here now these two load cases in design situation 1, what is, let's say, activated for stress strain, and you calculate stress strain, you get overall feedback for these two load cases. Let's activate it and calculate this stress strain analysis. And you will see you get here tables, stresses on solids. If you take a look on the input table now, what I jumped over just, we get here now the program will grab solids. It will activate it. Surfaces will be deactivated because they have no stiffness here. It will offer you also stress ranges, and finally also it will give you these solid configurations similar like we know it for member surfaces and line welds. Here you can say, please calculate me only this mesos part, and if you have here a special cast material, you can also check it against any user defined stress similar like for the line welds. And if you have also the task to calculate fatigue, you can activate here the stress ranges for solids. And if we recalculate it, you will get now 3 results for the solids. You will get stresses, you see here, stress ratios, and stress ranges. If we take a look on the stresses, you will see now we have an extreme here and the extreme here. What is coming because the program considers CO1 and CO2 at the same time and gives you the biggest forces of both. That's the difference if you watch only the results of CO1 or CO2. Then here we have 246. You get the stress ratio check where you see, okay, The extremes are under the allowed limit stress. Existing stress compared to limit gives a utilization. And if you need, like mentioned, ranges, so please compare minimum to maximum stress. You can activate it, and I did it now for solid, but you can do it also for members and surfaces and line welds. The program searches from the considered selection. Here we have only CO1 and CO2, the smallest and biggest stress on the same place, and gives you a range in between, and this will be output as colored skin above the model. And this brings me now to the end of point 3 I want to present today, where I want to repeat what's important here is you should see that stress strain analysis can calculate also, or can design also, solids with ranges. So now to sum up, stress strain is here to consider a basket of forces, for example, a DS or more DS for members, for member sets, for member representatives, for member set representatives, for surfaces, for line welds, for solids, and it can check the stress ratio, and stress ranges, and for a specific part also strains. And if you want to document all such things, we can use here, for example, our second model, our surface model here. Maybe make, if we remove types for surfaces, then it looks more suitable. And if we say, okay, how we can document all this stress strain stuff, we create a report, printout report, new report, give here a name, for example, stress check, and define what should be documented. In our case, let's start from scratch. So let's say we want to document from basic, from types for lines, the line welds. And in this model, we have line welds and surfaces. So the stress analysis, the global settings, the objects to design for stresses, the design situation, materials, thicknesses, surface conditions, and line welds. And from results, we check here stresses by surface and stresses by line on welds. And then you can create this document with all this information. The program will give you a document, let's say a styled document with a header, with a content, with all tables, what we just checked. So line weld joints, double fillet, continuous for millimeters, the global settings for the stress analysis, which objects, which forces, which materials, thicknesses, and the results with let's say check or marked with red if it's not fine. And if you say, okay, I have to extend it with pictures to get a nice document, no problem. You can say, okay, let's open the stress strain analysis and make a picture from the utilization of surface. And if you say, it's really blue and I don't see the focus, and you can say, yeah, let's visualize only the surfaces, what should be designed, and use here these so-called gray zones below the isobands. And this is a special feature which should help you to hide uninteresting parts. You can say here, please hide the 1 promille of uninteresting part, or maybe 5 promille, or maybe 10%. Then you see, okay, he hided now 10% of the uninteresting stress, what is not so close to the limit, and the rest will be visualized, and then you can make a nice picture without playing with the colored panel, and see directly where it's interesting. And you see, okay, interesting is here's the load introduction, here's the load introduction, here's the load overtake from this to this element. And now let's find a good placement in space and print the picture to report, where we say make window filling and with 3D option, for example. And now we move this picture into the report. And the same we are doing for line welds. So remove this, activate everything, and print again a picture with these diagrams of this utilization, and save and show, and get these two pictures in printout report. Now we have these two pictures here in printout report. Utilization of surfaces, utilization of line welds. And if you move this into a PDF, maybe on desktop, web, store, yes, then you get a document in Adobe Reader. Of course, this we already saw, content, these tables, but on the end we have these pictures. And as you see here, if your client will read and will look behind this structure, he can rotate it and can look below. So no problem. The same also for these line welds. He get much more information on a sheet of paper, what you can purchase to him. And this brings me to the end of my presentation, and I give back to Caroline.
Okay, thank you, Andreas, for your presentation. Now I briefly show you our website. Yeah, so here on our website you can find the free full trial version if you don't have it yet, for RFEM 6 and RSTAB 9, as well as R section and RVIN 2, and RFEM 6 and for RSTAB 9, the full trial version includes all the add-ons for the full 90 days. And then under news and events, webinars, you find the upcoming webinars and the past webinars, as well as the one which was presented today. Let's see where it is. Here, where I'll upload the recorded webinar the next days. And when you scroll a bit under here, you also can download the presentation slides, as well as the models which were used today in the webinar. And yeah, that's it from today's webinar. And if you now leave the webinar, there will be a survey. So it would be nice if you take the time to answer the questions. It won't take long. It's quite important for our quality management. And yeah, the worst score is 1 and the best score is 5. And yeah, so thank you for your attention. Thanks to my colleagues for presenting and answering the questions. And yeah, have a nice day, and hopefully we'll see you next time.